This is an application of linear approximation. So you have a continuous function, and you want to find the zero, but mathematically you can't find it well. Okay, so maybe it's some equation that you really can't solve. This is going to review some important concepts. So if it's a continuous function, we're going to look at our intermediate value theorem. And the intermediate value theorem, first, you have to know that it's continuous for the intermediate value theorem to exist. And anytime you want to use the intermediate value theorem, you have to make sure that you state it is continuous. Because the conditions have to be met. The three conditions for intermediate value theorem have to be met in order to use it. What does the intermediate value theorem say? Well, if it's continuous and you figure out one y value there and one y value there, and one x value here and one x value that goes with that one, and it's continuous, it's really an intuitive kind of thing, but it says that means that every value in between here, if I pick some random value c, it exists. And there has to exist an x value in between the two that you had that hits that c, which is important for x-intercepts. Because if I had a graph that was continuous, and I knew that there was a point below the x-axis here, and I knew that there was a point above the x-axis there, if it's continuous, since my x-axis is in between them, there is no way I can draw a line connecting those 2 points without going through my x-axis. It's really sort of common sense and intuitive. The hard part on the exam is making sure you state all the things for the intermediate value theorem to make that work. So we need to say that the x-intercept, well, one was positive, one was negative, so obviously your x-intercept, your y value of 0 is in between there. Therefore, there must exist some x value in between these two that gives us that value. So what Newton said is like, okay, if I choose some point on there, and I pick that point and I draw a tangent line, where my tangent line crosses the x-axis could be a good estimate. Not perfect, but it could be good. And this diagram is showing that. Okay? First of all, we start with this point. I want to find the actual x-intercept as this blue point. If I draw a tangent line from this first point, its x-intercept, I'll do it in green, is there. Is it pretty good? It's not bad. It's a little bit off the blue. This is Newton making an approximation. He's like, oh, that's not bad. He's like, well, what happens if I took this new point that you found, you said it wasn't bad, I find out what it actually is, which is right here, and I draw a new tangent line at that point. Then I get this as an x-intercept. Is it better? Yes. But Max, I'm not happy. I want it to be better. So Newton says, well, I go up and I find a new point here, draw a purple tangent line, and get a new estimate. And because of a linear approximation, the closer and closer you get to that point, the better your approximation would be. So what Newton would say, you can't figure out the x-intercept, try something, get closer, try it again, get closer. You're going to get really, really close. If it exists, and we can say, well, by, between here, if I started with this point And here, this point, obviously, if it's continuous, there had to have been an x-intercept in between. Sometimes, I'm not sure if your calculator is using Newton's approximation for finding an x-intercept or another calculus faster method, but do you ever find when you're solving for something on your calculator, you know the answer is like 2, and your calculator gives you 2.00000000001. And you're like, but I know it's 2. Well, your calculator was doing some sort of approximation method. And when it got close enough, it said, okay, I'm exhausted. I think it's close enough. Right? Can you imagine if your calculator had human traits, it's like start puffing a little bit, maybe some sweat dripping on the side. Because it gets to a point where it says it's close enough. It might be using something in this effect. So, how do we explain this in mathematics, right? We find our slope of our equation of our first line. We plug in our point, and then we find the x-intercept, and that's our new point. So just this idea, you found your first point, you find your first x-intercept. You now use that x-intercept to find another point, create a tangent, find a new x-intercept. I find this diagram, you get the idea, okay? This is the problem in mathematics. When we try to explain an idea without a diagram, this gets complicated to visualize. Oh, now I have C1, FC1. That's my new point. I find my equation of my line with my new point, C1, FC1, and my new derivative, F prime C1. And that becomes my C2. And I keep going, and I keep going. And I could simplify my equation, which you're never going to memorize this, but I guess you could. And you get better and better approximations. So, we'll do an example. All right, and you just keep repeating it. What's neat is if you keep simplifying it, that the nth approximation is simplified to always be the approximation right before minus its value over its derivative. Again, they are not going to ask you to memorize this formula. I just want to give you an application of this. And the important part, though, they will ask you lots of stuff on intermediate value theorem, so it's nice to review. There, we have an x cubed graph. You know what an x cubed graph looks like? You know that x cubed graphs, because they start bottom left and end, like this might be doing woo-hoo, something like that. And somewhere, I don't know where, maybe this has 3 x-intercepts. Maybe that's my x-axis. Maybe my x-axis is down here. I only have 1. Maybe I have perfectly 2. I don't know. I know it has at least 1. So it says, use the intermediate value theorem to show that the 0 exists in the interval from 2 to 3. So I figure out 2. I figure out 3. 0 is in between. And if I don't say this, I run into trouble. That is a condition for the intermediate value theorem. And they're pretty generous in, like, you don't have to prove continuity. Remember we had proofs of continuity as well? They're like, for most of your functions, if you say, since it's a polynomial function, I know it's continuous, they're like, okay, we're good. Almost all of the functions that we deal with are continuous. But you still have to state that. So because this, then because 0 is in between those two values, there must be a 0 or an x-intercept between 2 and 3 by the intermediate value theorem. So we're like, okay, how about 2.5? That seems like a good guess. You could plug 2.5 in. It's not going to give you 0. In fact, if you plug in 2.5, 2.5 into the equation is 2.875. It's not very good. The derivative at 2.5 happens to be 14.75. And I get 2.3 as a much better guess than my 2.5, according to this approximation. Okay? They're not going, well, I can't say not, but I'm like 99% sure they're not going to ask you this question on an exam because they're like, well, if we're asking you this as a calculator question, could you not just use your graphing calculator to actually find the exact x-intercept very quick? Then this is a bad technique to try to do when you could find it right away from your calculator. But just as an idea of linear approximation, we could then do a third point. And it's going to be our second point over its value. Oh, we were at 2 point, now we're at 0.23. C2 was pretty close. Oh, we should have went with 2.285. And C4 will be C3, 2.285. Look, we're 2.285, we were already at 0.0002. No, I had too many zeros on it. 002. There we go. Really close. And C4 is 2.28. Oh, wait, we were at 2.28565 and it's 57. Wow, we were actually really, really close already. I think my C4 is not necessarily the right number because it looks like I wrote exactly the same as my C3. It doesn't matter. The idea is what matters. In fact, you were correct to 2 decimal places, almost correct to 3 decimal places after only 3 approximations. Okay? So in Newton's age, where they had graphing calculators but no batteries, they had to wait so that they were waiting. They had this no, they didn't have graphing calculators. This is fast. Comparatively, right? Like, it's fast. They didn't have calculators, so they would still have to plug in 2.30508 into that cubic equation and do all that math mentally. Fast. But that's a lot of math. And they can get really close within 3 tries. So those 3 tries might take them 4 days of calculations, but that's okay. You'd have certain people that were like really good at the mental math. That's your job. Okay, here, I got another one. Okay. And they get the answer, and they're like, okay, now here's another one. So we can get an answer really, really quick. And that was 3 approximations was super fast. Consider the graph of sine x plus x squared minus 1. This is a great example because if I said solve for x, you actually have no method to do this without a graphing calculator. How do you get x by itself? If I plug in 0 for y, how do you get x by itself when one x is inside sine and there's another x in that same equation? That's messed up. But between 0 and 1, f of 0 is negative 1. F of 1 is 0.841. There's a 0 in between. And I would lose marks right here. Since sine of x is continuous, x squared plus 1 is continuous, adding them together will keep it continuous. Right? Only time you have problems is with dividing, because you might divide by 0. But if you have two functions, you add them together, subtract them, multiply them, and they were both continuous to begin with, your new function is continuous. I think on the exam, and you might watch this video and get mad at me, but if you say almost anything to try to explain that they're continuous, they'll probably go, okay, we'll give it to them. But if you decide not to say that it's continuous, whew, right? And it's such an easy thing to forget. Like I saw in the last exam, stating that it was continuous, the world average was like less than 1% over that mark. It's like, oh, such an easy, because it's so intuitive, you forget to write it down. First approximation, well, I would go with 0.5. .5 gives me 0.6441. My second approximation becomes 0.644107. And it's just a matter of continuing this. Here's the old one minus the old one's value over the derivative. You don't have to don't write these charts down. You can just continue it. You would have got, as your fourth approximation, 0.063673,265. And the actual one is exactly the same as the fourth one, to like 8 decimal places already. That's phenomenal. How close that value is. But again, if you are actually finding it, you have a graphing calculator, you'd be like, you would never use this approximation. But know that your calculator might be doing this, because if it only takes 4 tries, and your calculator is actually quite good at calculating, right? Social interactions, not so good, but it only 4 calculations, your calculator, I can do that. And it gives us an answer. Maybe that's all your calculator is programmed to do. Is this the actual answer? Or is this just Newton's fourth one and it said it's close enough? All right, so that is where we'll pause for today.